Question 2, Part C, Part 1. Prove by induction that cos theta plus I sin theta in brackets to the power of n equals cos n theta plus I sin n theta. We'll start by testing the base case where n equals 1. From the left-hand side, we have cos theta plus I sin theta in brackets to the power of 1, which equals cos theta plus I sin theta. From the right-hand side, we have cos of 1 times theta plus I times sine of 1 times theta, which gives us cos theta plus I sin theta, which equals the left-hand side. Hence, the statement is true for n equals 1. Next, assume the statement is true for some integer n equals k. In other words, cos theta plus I sin theta in brackets to the power of k equals cos k theta plus I sin k theta, and I've labelled this equation with an asterisk. We'll use that later on when we refer back to the assumption. Next, we need to show that the statement is true for n equals k plus 1. In other words, we need to show that cos theta plus I sin theta in brackets to the power of k plus 1 is equal to cos of k plus 1 in brackets times theta plus I times sine of k plus 1 in brackets times theta. Now, from the left-hand side, using one of our index laws, we can express cos theta plus I sin theta in brackets to the power of k plus 1 as cos theta plus I sin theta in brackets to the power of k times cos theta plus I sin theta in brackets. Now, from the assumption, we can replace this part of the left-hand side, that is cos theta plus I sin theta in brackets to the power of k, with cos k theta plus I sin k theta. So the left-hand side becomes cos k theta plus I sin k theta in brackets times cos theta plus I sin theta. And that's from the assumption, which was labelled with an asterisk. Expanding the brackets, we get cos k theta plus cos k theta times I sin theta plus I sin k theta times cos theta minus sin k theta times sin theta. You may be wondering where this minus comes from. And that comes from multiplying this I here with this I here. So I squared, of course, is negative 1. And that's where this negative comes from. Now I'm going to rearrange this expression and grouping certain terms together, and you'll see why shortly. So rearranging this expression, we get cos theta minus sin k theta sin theta, and then factorising out the I from this term and this term, we get plus I times, open bracket, cos k theta sin theta plus sin k theta cos theta, close brackets. Now, using trigonometric compound angle identities, we have a cos A cos B minus sin A sin B case. So this part of the expression can be replaced with cos of k theta plus theta. And this part of the expression here, so after the I, can be replaced with sine of k theta plus theta. So the left-hand side is equal to cos of k theta plus theta plus I times sine of k theta plus theta. And factorising out theta here and here, we get cos of k plus 1 in brackets times theta plus I times sine of k plus 1 in brackets times theta, which equals the right-hand side. That is the right-hand side here. Therefore, by mathematical induction, the statement is true for all integers n greater than or equal to 1. Part 2. Express w equals the square root of 3 minus I in modulus argument form. To help us find the modulus and the argument of w, we can sketch a right-angled triangle like so, where the horizontal side is the real component, the vertical side is the imaginary component, the hypotenuse is the modulus of w, and theta represents the argument. Firstly, let's find the modulus or the length of w. So we can use Pythagoras' theorem. So mod w is equal to the square root of root 3 squared plus negative 1 in brackets squared, which of course equals 2. to find the argument, notice that it's going to be a negative angle because it's under the x-axis or the real axis. We have theta is equal to negative tan of 1 over the square root of 3. And that equals negative pi over 6. So in modulus argument form, w is equal to 2 times open bracket cos of negative pi over 6 plus I sine of negative pi over 6, close bracket. And in abbreviated form, that can be written as 2 cis negative pi over 6. Part 3. Hence express w to the power of 5 in the form x plus iy, where x and y are real numbers. W to the power of 5 is equal to 2 cis negative pi over 6 to the power of 5, and that's using the result from part 2. Now using the result from part 1, taking into account this raising to a power of 5, that equals 2 to the power of 5 times cos of 5 times negative pi over 6 plus I sine 5 times negative pi over 6. Now 2 to the power of 5 is 32, and 5 times negative pi over 6 gives us an argument of negative 5 pi over 6. So w to the power of 5 is equal to 32 cis negative 5 pi over 6. Now to express it in rectangular or Cartesian form, I've drawn an Argand diagram and I've expressed 32 cis negative 5 pi over 6 as this ray here has a length or a modulus of 32. Its argument is negative 5 pi over 6. So I've formed a right angled triangle in quadrant 3. We need to take that into account. And the internal angle in this triangle is pi over 6. So the real component is going to be negative and the imaginary component will be negative as well. So the real part of w to the power of 5 is equal to negative 32 cos of pi over 6. And that equals negative 32 times root 3 over 2, which equals negative 16 root 3. And the imaginary component of w to the power of 5 is equal to negative 32 sine pi over 6, which equals negative 16. So w to the power of 5 in Cartesian form, or x plus iy form, is equal to negative 16 root 3 minus 16i.